Okay, yes, so I am today going to be talking about cuckoo hashing with negligible failure probability. This is my WPE2, and thank you all for being here today. So this, as I said, it is my WPE2, and so my WPE2 is based on the following three works. So Kirsch, Mitzenmacher and Wieder were the first ones to introduce cuckoo hashing with the stash, and I will be presenting their results and also presenting their analysis, somewhat summarized, but the general gists of their analysis. And then I will be presenting the result by Goodrich and Mitzenmacher, which use the same framework as Kirsch et al., but were able to extend this such that it could be applied to oblivious RAM. And I'll be showing a bit how they do that. I will unfortunately not have time for the work by Müller, Dietz, Feldinger, and Waldfeld, which showed an alternative way of looking at this analysis, which is quite elegant, but yes, didn't have time for it in my presentation, but you can read more about it in the WPE2 write-up. And I'll also be touching briefly on the titer analysis that I present in my WPE2, which is based on the analysis of Kirsch et al., but yes, improves it both concretely and asymptotically. Great, so firstly, I'll talk about what problem we're trying to solve. So a cuckoo hash table is a type of hash table, and a hash table is an implementation of a dictionary. So a dictionary is a way of efficiently storing data in memory. So imagine we have n elements and we want to store them in memory. Normally we talk about the elements having keys, and which we use to look up the values, and then in the database or in the memory, we store the values, but for the sake of this presentation, we can forget about there being keys and values, and we'll just say we are storing elements in the table and looking up elements. So we want to be able to do this efficiently. Specifically, we want to be able to find items without needing to search through a lot of memory, and we would like the amount of memory that this entire data structure takes up to be order n, where n is the number of elements, and the unit of memory is the size of each element. So a good tool for being able to do this is a hash table. So hash functions are deterministic functions that produce seemingly random output. And for the sake of this presentation, I'll assume that to an adversary that does not know the hash function, the output seems as if it's distributed uniformly at random. This is an assumption that's made by basically all of the papers in this area. So given such a function, and we want a hash function that takes as input this set of elements and produces as output an index in the range of the table. And so we simply hash an element and store it in that index in the table. In doing this, we can easily place elements in the table, and we now know exactly where to find them. We simply need to search for an element, we simply hash it, look in that location, and we find it there. However, we quickly encounter a problem that multiple elements might hash to the same location. Specifically, there is the birthday bound, which states that if the memory is less than order n squared, then collisions will happen with high probability. And since we want to have order n space, collisions will happen with very high probability, and so we need some way of dealing with them. A standard way of dealing with them is to use chaining. So for instance, we could create a linked list object, and each location in the table, as well as being able to store an element, can store a pointer to another location in memory. And so using these pointers, we can create a linked list of elements. And so if we want to search for an element, we search in that location in the table. And if it's the beginning of the linked list, we traverse the entire linked list until we find the element. This works very well for most applications. It's pretty simple, straightforward, and even though sometimes you have to traverse the chain in order to find the element you're looking for, the expected amount of memory access is still low. The expected amount of memory you have to use for the entire table is also quite low. And so for most data structure purposes, for most algorithmic purposes, this is a very good data structure. However, imagine there's some cloud service provider, let's call it Gaggle, and we want to store our data on Gaggle's server, but we don't want Gaggle to learn anything about our data. Now, to start off, we could encrypt our data, and that is a good start. However, the server Gaggle might still be able to learn information about what we've been querying or about the relationship between our queries and what we have stored in our table. So for instance, in this example, say we were to first search for the penguin. So that would mean we would first look in the flamingo location, and then not finding it there, we would traverse the linked list and search in the penguin location. Now imagine after that, we search for the flamingo. We search in the flamingo location and we find the flamingo and we stop. Now Gaggle knows that we must have found something. It doesn't know it was the flamingo because everything was encrypted, but it knows that we found something in that location. And so it knows, since we stopped searching after we found it, and so it knows that whatever we were searching for in that query must have existed in the database, in the table. So we would like some way of avoiding this. A bit more formally, we want a data structure such that the physical access patterns reveal nothing about the table contents, about the queries, about any relationship between the table contents and the queries. And we want this to hold true except with negligible probability. A bit more formally, that means we want the advantage that the adversary has when they have access to the physical physical memory accesses. We want the adversary in distinguishing sets of table contents and queries from each other to be negligible. Now, I've said that we're going to be using hash functions, which are deterministic functions. So if the same element is queried twice, the same locations are going to be accessed again in the memory. And so this security guarantee will only hold given that the same element is not accessed twice, that there's no repeated queries. I'll later be talking about oblivious RAM, which is a way of getting around this limitation and allowing the same query to be repeated multiple times. And another caveat that I should mention to the security is that the adversary can obviously see how many queries are made, and so the adversary would obviously be able to distinguish access sequences with different numbers of queries, and so we add an additional condition that the adversary should not be able to distinguish query sequences of equal length. So given these security parameters, these security conditions, we say that a data structure that satisfies these is an oblivious hash table. And we also would like it to be efficient. Specifically, we would like to be able to construct oblivious hash tables that only use order n space. Now, there's
is there no requirement on the computation cost?
So I'll be presenting a few different protocols. The ones that have negligible failure probability will actually require logarithmic number of accesses. But I'll also be talking about ones that have less than negligible probability that have constant number of accesses.
Cool, thanks.
So first off, we'll look at cuckoo hashing, which attempts to solve this problem. So in cuckoo hashing, instead of having one table, we have two tables. I should mention also there are a lot of different variants of cuckoo hashing. The one I'm describing is the original one that was presented by Paget and Rodler in 2001. So the way it works is we have two hash tables, each with epsilon n space, where epsilon is some constant greater than 1, and n is again the number of elements that we would want to store in this table. Now each element, instead of only having one location it can be stored, has two locations that can be stored. And I'll show using which table it's closest to, which location we store it. So we can simply store an element in each of one of these two locations. And whenever we query, we simply query these two locations. And if we find it in either of these locations, then we return the element. Now we can see if there's a collision in one of these tables, but not the other, we don't have a problem. Because, so for instance, we can store the flamingo in table 2 and the robin in table 1, and everything is still fine. And yeah, we can continue storing elements in this way. So there are and we can see even if 2 elements are stored in the same 2 locations in both tables, we can satisfy that as well, because one of the elements can be stored in one table, one of the elements can be stored in the other table. Now there are 2 different ways you can think about this table being constructed. One is if we know all of the elements we want to store in the table at first, then we can use some kind of matching algorithm to find an optimal allocation of items to table locations. And this essentially becomes can be treated as a 2-SAT problem, because you're basically having conditions if this item is stored in this location in the table, this item cannot be stored in this location in the table. So yeah, we can efficiently find an optimal allocation if we're given all the elements beforehand. If we're giving the elements one at a time, then we have to have some dynamic way of constructing this table. But we can do that simply using the following process. And this is also where the name cuckoo hashing comes from. It comes from cuckoo birds, which a cuckoo bird will lay its eggs in another bird's nest, and whenever the eggs hatch, they kick out the eggs that were from that nest. And so similarly, we can do an insertion by storing an element in one of its 2 locations, and if there was something in that location, that thing is kicked out and has to move to its other location, and it might in turn kick something out and move it to its other location, and so on. Now, this works a lot of the time, but say we try to insert this parrot, then say we put it in table 1, we would kick out the robin, store the robin in table 2, kick out the flamingo, store the flamingo in table 1, chick moves to table 2, penguin moves back to table 1, and now, but the flamingo has already had to move. So we can see there isn't going to be a way that we can store all of these elements in the table. And we can see that this pretty easily because now in this bottom section of the table, we have 5 birds and we want to store them in 4 locations. And so by the pigeonhole principle, one of the pigeons doesn't get a hole. So is this a problem? For a lot of cases, it isn't really a problem. So for most data structure situations, we can simply rebuild the table if this occurs. So Dagger and Rodler showed that if you insert n elements, the probability that there is a build failure like this is 1 over n. And so yeah, there's a 1 over n probability that you would have to rebuild the table, but this doesn't affect the asymptotic cost of inserting elements or of building cuckoo hash tables. However, for the case that we care about, we also need that no events leak anything about the access pattern. Now,
I have a question. Since you mentioned earlier that the hash functions were deterministic, when you rebuild the table, won't you end up in the same situation? Or
you need to pick new hash functions and reinsert everything.
You have a family of hash functions, out of which you choose, right?
Yeah. So you pick the hash functions from a large family such that the outputs seem random. So for crypt security applications, if we have a rebuild, there will actually be a problem that's not entirely obvious. So at the point that there's a rebuild, the adversary learns that a rebuild has occurred, but that actually doesn't leak anything yet because the adversary doesn't know what the hash functions are. They don't know what the table elements are, and so the fact that a rebuild has occurred doesn't leak anything to them. However, this means that if the table is successfully built, the adversary knows that there cannot be this kind of, that every element has a unique location that it can be stored in. So now let's imagine that instead of this referring to the items that are inserted into the table, this refers to items that are queried.
Sorry, one question about the adversary's power here. Does the adversary know the actual hash functions being used right now?
No.
Would that be a huge, I mean, would it be impossible if the adversary knew the hash functions to protect the information? Or I guess they don't.
Yeah. At least they would be able to distinguish between, for instance, two queries, because they can see that the outputs of the hash function, or they can see which locations were accessed. So it's absolutely essential. The adversary knows nothing about which hash functions are being used.
Yeah.
So if another set of elements is stored in the table, and this is the set of elements that are queried, the adversary can now see, based on the physical access pattern, that this set of elements that were queried could not all be in the table, because if it were, the table would have had to have been rebuilt. And so, and built in a different way using different hash functions. And so the adversary learns that if it sees this kind of access pattern that would have caused a table rebuild, that the items that were queried could not all exist in the table. And so now the adversary, this failure is not some additional computational cost to the data structure. It's actually a security failure where the adversary has been able to learn something about the access pattern. And so now the fact that this event occurs with probability 1/n means that there is some non-negligible advantage that the adversary has gained in learning about the access patterns and being able to distinguish them.
Sorry, quick question. Earlier, when you were discussing oblivious tables or oblivious hash tables, that was mostly in the context of querying. But now you seem to be talking about it in the context of inserting objects into the hash table, because that's when you deal with these collisions by reconstructing the table, no?
Okay, yes. So the probability that the adversary learns anything from the query sequence should be negligible. So it's not, I'm not really talking about how the table is constructed, but about just the accesses.
But presumably, that's why I'm slightly confused at the moment, because you're essentially saying if an adversary observes this ping pong pattern of accesses, that's going to leak in, and furthermore, after that, a table has to be
no. So it's not that the table is rebuilt after it, it's that they know that the table must have been built in such a way that this sequence wouldn't have occurred if all the elements were stored in it. So the leakage doesn't come from the table rebuild, the leakage comes from the querying after the fact, based on the knowledge that the table must have been constructed such that this pattern wouldn't have occurred.
Okay, so you're saying there's a precondition to this table, which is that it was generated in such a way that there are no collisions.
Yes.
And given that precondition, I can already make inferences about what a client might be querying, because...
So in the case that the client queries a set of elements that are not in the table and they have this kind of pattern of too many collisions, then the adversary will learn that those items could not have all been stored in the table.
Okay.
But my question is, if the adversary doesn't know the hash function, he just learns that there's some set of elements that could not all be stored simultaneously in the hash table, but doesn't know anything about them per se, right? I don't understand what the security leak is here.
So it was important not just that the adversary doesn't learn what was queried, but doesn't learn any relationship between what was queried and what was stored in the table. And so in this case, the adversary learns that the set of items that were queried could not all be stored in the table.
Let's see. Whatever they be.
Whatever.
I don't know anything about the items themselves, but just knows it. I see. Okay. Okay.
Okay. So yeah.
So just Sampad, you can formalize this, right, with a simulator or like an attacker, right, who's going to say the attacker gets to generate 2 possible tables and, you know, 2 possible sequences of, or then a sequence of accesses that's trying to determine which table, like which world you were in. Like if you wanted to think about this as an indistinguishability game, right? Imagine the indistinguishability game is I generate, you know, 1 of 2 databases, and then we insert them into this table. And then I get to generate a sequence of queries. And based on the access pattern of these queries, I have to determine which, you know, which table I was interacting with, which set of underlying elements I was interacting with.
Great. So now we need to find a way to bring this probability of the security failure lower. So Kirsch et al. Proposed that we could add an additional area of memory called a stash, and any data that wasn't able to be stored in the main table can be stored in the stash. Now, whenever we query an item, we query its 2 locations, and we also have to query the entirety of the stash. And we need to query all of the stash every time, because if we stop early whenever we find something, that would leak that we found something. So this means that the number of physical accesses per query is now increased to 2 plus s if the stash is of size s, but this does significantly reduce the failure probability, and specifically Kirsch et al. Showed that it reduces it to order n to the negative s for any constant s. So now I'm going to present how they were able to prove this, present their analysis, not in complete detail, but the general principles of it. So firstly, observe that this problem can be treated as a graph problem. I've already been showing the lines of the 2 locations that an item can be stored as lines or as edges. And we can then consider each location that items can be stored as vertices. So now we have a bipartite graph with epsilon n vertices in each part and n edges. And this is, again, this is also a multi-graph, i.e. there may be vertices that have more than 1 edge between them. The edges are chosen randomly, i.e. each edge has 1 endpoint chosen uniformly at random from one part, and 1 vertex chosen uniformly at random from the other part. And so now this distribution of graphs represents the distribution of accesses that we would have in a Cuckoo hash table. So now how do we describe how large the stash would need to be? So let's observe, for instance, before we inserted the parrot, we were able to store everything in the table. And so if there's 1 cycle in the graph, we can pick an arbitrary orientation of that cycle and assign each edge to the vertex after it in that orientation. Then for remaining edges that are part of that connected component, we can assign them the vertex that is 1 further away from the cycle. And so this shows that if every connected component in the graph contains at most 1 cycle, then we can assign each edge to a unique vertex. If there are connected components that contain more than 1 cycle, then these will not be able to be stored, simply due to the fact if a connected component contains more than one cycle, it will have more edges than vertices. And so it is impossible for each edge to have a unique vertex assigned. So let us define the minimum number of edges that need to be removed from a graph such that each connected component contains at most one cycle. We'll call that number the excess of the graph. And so now we can see that if we were to remove all of those edges, then i.e. place all of those items in the stash, then we would be able to successfully assign items in the remainder of the table. And similarly, if we were to not remove them, then there would be at least one item that would not be able to be stored. And so the size stash that we need is exactly equal to the excess of this graph. And so now we have this well-phrased graph problem of, given this distribution of graphs, what is the bounds on the excess of the graph? Some notation that will prove useful later. Given a vertex V, we refer to CV as the component, the connected component that contains V. And gamma CV is the cyclotomic number of CV. And excess of CV, EXCV, is the excess of CV. So the one thing that makes it a bit difficult to solve this problem is the existence of edges is not independent. So for instance, if we were to look at the first three vertices in the left part of this graph and see that they have only one edge that they are connected to, we would learn that in the remainder of the graph, the number of edges is more, and so the expected number of neighbors that each vertex has is more than it was in the original graph, and this makes analysis a bit difficult. Yeah, so if we find, because there are exactly n edges, if we find an edge between one vertex pair, then edges are less likely to exist between other vertex pairs and vice versa. So the first thing that Kirsch et al. Do in order to address this is, instead of having exactly n edges, they choose the total number of edges according to a Poisson distribution. Now, the Poisson distribution has the property that if there are a number of different variables, each chosen according to a Poisson distribution, then the total, chosen according to independent Poisson distributions, then the total is also a Poisson distribution. Now, this property actually works in reverse as well. If we have a total number of elements chosen according to a Poisson distribution, and we assign each element a bin chosen uniformly at random, then each bin will also have a number of elements chosen from a Poisson distribution. So now if we choose a total number of edges according to Poisson lambda, and then for each edge, we basically treat each pair of vertices as a bin, then the number of edges between each pair of vertices will be distributed according to this Poisson distribution, and these distributions will be independent. One other thing that is helpful to notice is also the number of neighbors of a vertex will also be distributed according to a Poisson distribution, namely Poisson lambda over epsilon n. And so then they pick lambda to be a constant factor larger than n, but a constant factor smaller than epsilon n. And because the Poisson distribution has pretty tight tail bounds, this means that the probability that Poisson lambda is less than n is negligible in n. Now, why does this allow us to reason about the graph we had before where there were n edges? Well, we can, let's ignore for now the case that Poisson lambda produces a total number of edges less than n. Assuming that the total number of edges is greater than or equal to n, we can just look at the first n edges, and then these n edges will be assigned vertex pairs uniformly at random. And so the distribution of these n edges will be exactly, the graph just looking at these n edges will be distributed exactly according to the graph that we had before, where we had exactly n edges. Now, what's the only difference? The only difference is that we have added some particular extra edges, perhaps on lambda minus n additional edges have been added. But if there's any property of the graph that only at worst increases whenever edges are added, then this property will be larger, or specifically it will be stochastically dominated by the case whenever we're choosing graphs from this Poisson distribution. And so the excess is a property that will only ever increase if you add more edges. And so if we find some probability bounds of the excess in this Poisson version of the graph, then these bounds will also apply to the original version of the graph where we had exactly n edges. And of course, there's also a small probability, negligible probability, that Poisson lambda is less than n, so we just can add that to the failure probability at the end.
Will the difference between the two be a very loose bound? Or is the bound decent? Or is this something you're going to get to later?
Like
if I derive a bound for this Poisson graph that you're showing here, how good of a bound that is in relation to the original graph with end edges? Is that a very loose bound, like a very loose upper bound, or is it a pretty decent bound?
It's a pretty decent upper bound. And we can see that, for instance, because the Poisson distribution is tight on both sides. And so the probability that lambda is greater than, say, epsilon n is also going to be negligible. And so if we just had a different value of epsilon, which was larger, then it would be the Poisson would it'd be like equivalent. So it's equivalent up to like small changes of the constant.
Okay, cool, thanks.
Okay, so now we have this very nice property that the existence of edges is independent. And so then we can proceed. The way I describe this is slightly different from the way Kirsch et al. Describe it in their paper, but it's slightly simpler. So we can do a breadth-first search starting from a random vertex. And we continue the breadth-first search until we're done. And this is, now we have found all of CV. And again, I remember I said that the total number of neighbors was distributed according to Poisson lambda over epsilon n. And we also had that that lambda was some constant factor less than epsilon n. So lambda over epsilon n is less than 1. And so the expected value of neighbors that each vertex has is less than 1. So that means that this graph will die out, that this tree will die out pretty quickly. And more specifically, they show that the probability that this tree is of size k is less than or equal to beta to the k, where beta is some constant less than 1. So the size of the tree decreases exponentially. The probability that a tree is a certain size, a component is a certain size, decreases exponentially in the size. So given that we have a tree of size, a component of size k, how do we bound the excess of this component? Well, let's look at which pairs of vertices could have edges between them. Now, recall again that we have, this is a bipartite graph, and so the total number of vertices that could have edges between them is k squared over 4. So it will be maximized whenever there's k over 2 vertices in each part, and in that case, there will be exactly k squared over 4.
I suppose you could do a further refinement, noting that this is a breadth-first search tree by knowing that the edges can only go between successive levels, but I guess it doesn't do much for you in the worst case, right?
Yeah. So in the worst case, you have to have one vertex at the top but you have, in theory, k over 2 in the next, and then k over 2 minus 1 in the last.
Yeah, then you get pretty much all the possibilities.
There is, and I've thought about this a bunch, but haven't been able to find anything to make it a bit tighter. The shape of these trees is not going to be worst case, and so these are called Galton-Botzen trees, and there is a lot of research about what kind of shape they have bounded on their size, and given that, I feel you could possibly make the bounds tighter, but I haven't been able to figure out how.
This is just one case of a birth-death process or something. Is it like a birth pure? Is it like a stochastic process?
Yeah, like epidemiology.
Yeah. I mean, can you not bound the? I mean, with high probability bounds on the degrees of vertices to show that the trees that would be problematic are the ones that expand greatly at the first vertex, right? And then are very shallow, but still big. And if you could show that that has a low probability, or I don't know, maybe. Okay, this is not for now. Let's offline or later. Yeah.
Yeah, I feel like there is a bit more that can be done, and we can talk about it more later. So each of these pair of vertices will have a number of edges distributed according to Poisson lambda over epsilon n squared. Actually, stochastically dominated by Poisson lambda over epsilon n squared, because, for instance, some of these are conditioned on the fact that we know that there's at least one further. We're looking at the number of extra edges that exist, conditioned on there being at least one edge. But anyway, all of them will be stochastically dominated by lambda over epsilon n squared, and so the total number of additional edges will be distributed according to Poisson k squared lambda over 4 epsilon n squared. And now each of these edges would add one additional cycle to the graph, or phrased another way, these additional number of edges that exist is exactly the cyclotomic number of this component. And so this now gives us a bound on the size of the cyclotomic number of a component given its size. And then we can simply do some math and put these equations together. So we can apply a standard bound on the Poisson distribution to get this result. So the result in Kirsch et al. Is actually slightly looser. It's the one that I show on the right, and I'll continue using that one later for consistency with that paper. And
so the one on the left is your tightening?
Yes. Okay. And so now we can combine these two equations, the top equation and the bottom one, to create a bound on the probability on the cyclotomic number of a component. And then if t is any constant, we can simply take the n to the negative t term out of this summation, and we will have some summation over a polynomial in k multiplied by a negative exponential in k, which will be some constant, provided t is constant. Now, if t is not constant, then the degree of this polynomial of k is dependent on n, and so the summation term would no longer be constant, and so this is no longer order n to the negative t. And based on what we know about the relationship between the cyclotomic number and the excess, for any s greater than or equal to 1, the probability that the excess of a component is greater than or equal to s is order n to the negative s plus 1. And I'm skipping there's a number of things that have to be shown that I'm skipping over in order to go from this to bounding the excess of the graph. So in brief, you have to add up all of the possible ways that these excesses could be combined in order to create an excess of the whole graph. And you also need to consider the fact that excesses of different components are not independent, but they are actually negatively correlated, because a large component is going to use up more of the vertices, and so leave less vertices as potential neighbors for other components. So yeah, I'm kind of skipping over the details of the math there, but they do show that, therefore, for any constant s, the probability that the excess of the entire graph is greater than or equal to s is order n to the negative s. So this is an important result. In practice, it allows you to reduce the failure probability substantially. However, it still isn't negligible, so s is constant. And there's actually also another problem. In a lot of applications, n might not actually be that large. So I mentioned previously oblivious RAM. So oblivious RAM is a way of having something with the same security properties as the oblivious hash table, except you can access the same element multiple times. And a common way of doing this is using the hierarchical method, in which there are a number of geometrically increasing oblivious hash tables. And essentially, each item can be queried in each hash table at most once, and hash tables are rebuilt when necessary in order to make sure that you can always find each item in at least one of the hash tables. Now, some of these oblivious hash tables might actually be very small. So if there is a total of W elements in the oblivious RAM, the smallest hash table in a lot of these schemes will have size log W. And so if n is equal to log W and s is constant, then n to the negative s really isn't that small at all. So we would like to have an oblivious hash table which can have failure probability negligible, not just in the size of the table, but in the size of some other term, which might be like exponential in the size of the table, or rough, like where the size of the table might be polylogarithmic in the term that we want the failure to be negligible in.
So to understand what you're saying a little bit more,
yeah.
It's not that n being small is the problem, but the fact that the hash table sort of size epsilon n for some constant epsilon, and when n is small, epsilon n will be small. That's really more of the problem, isn't it?
Yeah, so if we want a constant ratio between the size of the table and the number of elements that we put in it, the failure probability is higher for smaller tables.
Right, and it's the table size, because I can always pad n with all kinds of dummy elements that I hash in. That is not the problem. The problem is the hash table is small, right? Really.
Yeah. Well, if we want to have this property that of the number of real elements stored in the table, that the memory is order n in those.
Yeah.
But again, just right, it's not the epsilon though. It's that you want something that's negligible in the total number of elements in all of the hierarchy of tables. But that means that you need it also to be negligible for the smallest table, but that smallest table has a number of elements that's logarithmic in the total number of elements in all the tables.
Right. Yeah. That's it. Yeah. Right. Again, it's okay. No, I understand. There's a monotonicity with n that I was worried about, but in this kind of context, it makes sense. Yeah.
So Goodrich and Mitzenmacher wanted to create an oblivious RAM protocol that was based on cuckoo hashing. And they had this problem, but they looked more closely at the analysis of Kirsch et al. And they realized, so this is exactly the equation that we had 2 slides ago. And they realized that beta to the k will be negligible when k is omega log squared w. This is negligible in w. And the term on the left will, so if we say that n is omega log to the 7w, then k cubed over n will be if k is then order log squared w, then the term on the left will be order n to the negative t over 7. And so then they're able to show from this that the probability that the access of a component is greater than or equal to s is less than or equal to c n to the negative 1 negative alpha s. C and alpha are constants. Yeah. And then using pretty similar techniques from before, they're able to use this to bound the excess on the entire graph. then show that it's less than or equal to n to the negative omega s. But they do have this condition that n has to be omega log to the 7w. And so just to reiterate, this is now, say s was equal to log w, and n is polylogarithmic in w. This term n to the negative omega s will be negligible in w. So this is a pretty significant result, and a lot of later oblivious RAM protocols use this result. So if you ever see a log to the 7 term in an oblivious RAM protocol, this is where it came from. But in some ways, it's not entirely satisfying. They don't explicitly state what the constants are in the negative omega s term. And also having this restriction that this condition only applies when n equals omega log to the 7w means that for oblivious RAM protocols, you need to have some other kind of tables for n less than log to the 7w. And in practice, for values of w that you might care about, log to the 7w is probably might be larger than w. So this theoretically is a very significant accomplishment and was built upon a lot. But if you want to be able to produce concrete oblivious hash tables or oblivious RAM protocols, the fact that it has this condition and it doesn't explicitly state the constants is very limiting. So I won't go into detail but I present a tighter analysis in my WPE2, and I show that the probability that the excess of a component is greater than or equal to s is epsilon2, epsilon3, s plus 1 over epsilon n to the s plus 1. And epsilon2 and epsilon3, I don't write out exactly what that equals here, but in my WPE2 write-up, I state exactly what these are in terms of epsilon. And so this provides concrete bounds on the excess of a given component, and then this can be used to get concrete bounds on the excess of the entire graph. Where again, epsilon 4, epsilon 5, and epsilon 6, I don't state what they are here, but in the WP2, I state explicitly what those are in terms of epsilon. And also this epsilon e to the negative epsilon 6 n term, which looks kind of weird, that comes from the Prassamization.
But all of this is still with assuming that n is log w to the 7th at least.
No. So these are concrete bounds that apply in general.
Apply in general. Oh wow, I see.
Yeah. And so now we can think about, given specific ranges of s and n, what will this mean? So if s is log w and n is omega log w, lowercase omega log w, then this will be negligible in w. And we will also be able to compute exactly what the probability of failure is because we know the explicit constants.
But s has to be theta of log w. Could it be log w, for instance?
So if s was log w, then n would have to be larger relative to w. So if s is theta log w, then all that you need for the fraction, for this to be negligible, is for this fraction to be less than 1, like less than any constant.
Yeah.
But yeah, there are other configurations that you could make it negligible. Great, thank you very much, and I will take any questions.
Thank you.